Hello everybody! Today we're going to go over AnteHash2 and the inner workings that power it. To start, let's talk about hashing that we used in the first AnteHash. AnteHash took the SHA-256 hashing algorithm and created a hashed output from the message. Hashing is where we take a text and irreversibly scramble it to a hashed output, in which the SHA-256 algorithm is a 256-bit output. The great thing about this is that we no longer know what the input was and it can be kept a secret, while the only way to get the same hashed output is to know the exact input. This is the basis of a lot of password storage and other secret keeping where we want to be able to verify the validity of the input yet not have it be revealed. However amazing this sounds, hashing isn't perfect. We have to assume a few things about it. One, the hashing is only one way, where we cannot use the output to get the original input back again. Being able to do so would defeat the whole reason for hashing. Two different messages don't hash to the same output, known as collision. This is because we're assuming that every output is unique, so if two inputs come to the same output, then we would assume they're the same. While there are a possibility of 2 to the 256 different outputs, it technically isn't infinite, and while it is possible to have a collision, it is highly unlikely and improbable to happen. And third, extending from the collisions we just mentioned, it is possible to try every single combination of the 256-bit output. We would eventually land on the correct output of the hash and thereby break it. But this is dependent on how fast we can check every combination, which at current computing levels takes an unreasonable amount of time. But we can presume that as computing power increases, this time decreases, and it's possible that it can decrease to a point where it's doable within a reasonable amount of time. Now we move to the new feature that AnteHash2 brings, the relayer. The relayer is a product that we can take a message and automatically put that on-chain. Using that functionality, we take all prior commitments and build a Merkle-Patricia tree. Taking the root hash of that, it compares the hash to the on-chain root hash, and if they're different, that means there's been a new commitment and it will update the on-chain root hash to this new root hash. This following image demonstrates a brief representation how commitment A gets added to the Merkle-Patricia tree and how the new hash is created and uploaded. Using these new features added in AnteHash2, this allows us to place messages on-chain without costing user gas in a compact way. Once created, these messages can be retrieved and referenced again to be used. Additionally, using the succinctness property of Merkle-Patricia trees, we can generate a proof to prove if a message was placed on this chain before. These properties allow us to build potential applications on top of these features, such as being able to place even broader antes on-chain as opposed to our previous antes which were in the form of smart contracts. And expanding on that, we can even place successes or completed achievements on-chain, almost like a record. The proof of past commitments also allows us to build application on top of these verifications using the permanence of the blockchain. Thank you for sticking around and come join us on Discord to continue the conversation.